international education and
This call
training.
is now being recorded.
I am director for international and education training academy based in Liverpool, northwest of England, as well as I am a freelance professor of petroleum engineering. I have a big deal of lecturing, consultancy, field work, book and training writings. Today, I will talk very much about reservoir properties because this is an important subject for petroleum engineering and people work in petroleum engineering as well. My agenda will have a short review about the oil and gas in India. Then I talk about the role and the job of reservoir engineer, the type of the reservoirs, oil traps. I talk about the rock properties, fluid properties, the parameters we need to look into, such as pressure, temperature, saturation. How do they estimate a reserve, and also how they develop a reservoir. I will try my best within these 90 minutes to specify on these and talk only about these points as much as I can. Although I doubt it, I finish it, but I will do my best. I prepared for you more than 259 slides. I will share these slides with you later on by email. I will email it to the principal. So the little history about oil and gas in India. India has an old history about oil and gas. In 1889, they discovered the first oil deposits or reserve in Assam state. I think that Assam state is very much into the northeast of India. And then they discovered the gas in 1960, about 60 years ago. They discovered it also in Gujarat and also in Assam. So the history of oil and gas in India is an old history, and they know very much. There's a good names for Indian oil companies working around the world, such as ONGC, as well as on Oil India companies. They are working around the world. So there's a history of oil and gas in India. And this little map, small map, show you the location of the oil and gas, both onshore and offshore, present in India. I think that's your area, if you correct me. You are here, aren't you? You are in Rajasthan. And you have an oil field as well here, which is an onshore oil field. Maybe Assam, this is Assam, the northeast, is rich with oil and gas, but also your area also rich with oil and gas. You have oil and gas also in the offshore, both on the east and west, such as in Mumbai Bay, they call the deep water. Offshore, you have also in Chennai area, as well some offshore oil and gas. Most of the offshore are gas, and most of the oil will be onshore. So you have some oil and gas in India, which need to be developed and need to be put into actions. This map of India as well tells us the location of the oil and gas. The green one is oil. The red star is gas. So we have gas, for example, in the east offshore. And also we have some gas in the west side, near Mumbai. And again, I assume this is your area. This is Rajasthan area. where you have also oil and gas in your area, which is near to the border of Pakistan. Again, Assam, where you have the ONGC is very active there, working in that area. So this map in front of you give you an idea about the distribution of oil and gas in India and little history about it. Yes, it is some of them recent history, 2004, 5, and so on, but for sure you have oil and gas. As a statistics, as a data in this table, I show you that the location or the name of the places where you have oil and gas. On purpose, I put Rajasthan in yellow shadow or yellow background because that's your area. That's where your college is located in Rajasthan. So you have about 4% of India oil is in your area, and about 3% of gas of India is in your area. So in your Rajasthan, you have both oil and gas with a certain percentage of the total. Yes, maybe the richest area is Assam. They have a good percentage of oil and gas, but your area is rich also with oil and gas. This is a little review about oil and gas in India, just to give you an idea about what do you have. I got my data from certain books I use. Reservoir engineering, that's our topic today. The reservoir is a branch of petroleum engineering. For example, in your college now, you teach petroleum engineering, and the students will learn something about the reservoir. In the reservoir, people will study something about rocks, geology, traps, physical and chemical properties of the hydrocarbons, crude oil and natural gas, water of the reservoir as well. So it is a subject that deal with the what we call upstream. Usually the oil or the petroleum industry are classified into 3 categories: upstream, downstream, and midstream. Upstream, including the reservoir and the drilling. So reservoir and drilling is upstream. A production, surface production, for example, is a downstream. Piping, transportation is a midstream. Refinery is a downstream. So reservoir is branch of upstream. And reservoir engineering, also they look into the how much oil in place, reserve, how do they calculate it? And also they look into the properties of the oil inside the rocks, such as the, is it natural gas? Is it wet gas, dry gas? It is heavy oil, light oil. So they do PVT and also economic studies. The reservoir engineer also later on, they do something with the enhanced oil recovery, EOR, such as water injection, gas injection, to maintain the pressure of the reservoir. So it's a quite important topic within petroleum engineering is reservoir. If you are a reservoir engineer, if you graduate, and then you do graduate as a petroleum engineer, and then you specialize as a reservoir engineer, maybe MSc reservoir engineering, or you will specialize and work as a reservoir engineering. This is some of the roles for reservoir engineer. A reservoir engineer will be responsible for estimating how much oil in place, forecasting the development, what do I need to develop in my reservoir, my field. By the way, oil field and reservoir. Reservoir is smaller inside than oil field. One oil field may be made of 3 or 4 reservoirs. Reservoir is the name of the rock that having the oil inside it. Reservoir is a French word, which means a tank or a vessel. So that rock having oil inside it, we can name it as the reservoir. Sometimes say reservoir formation reservoir. The reservoir engineer is the person who can estimate how much oil in place. He could talk about performance of the oil well. He will talk about, shall I do water injection, enhance oil recovery or no? Do some economic as well about price and cost and current values and net present value, the CapEx and OpEx, capital expenditure and operating expenditures. All these are the job of a reservoir engineer. Also, a reservoir can talk about petrophysics studies. He may study something on the rock properties, fluid properties, PVT. So it's a wide activities a reservoir engineer can do. I do encourage some of you to specialize in the future to be a reservoir engineer. Maybe doing MSc in reservoir engineering, maybe get a job in reservoir engineering or so on. So I got subject and very important subject in petroleum engineering. This is also a little history about oil in the world, not only India world. So the depth of reservoir sometimes could be shallow, only 40 feet. You can get oil out of it. Sometimes you drill up to 21,000 feet, as in the North Sea. Sometimes now also 26,000 feet, 26 or 20. The deepest oil well, actually in the North Sea, the deepest oil well in Gulf of Mexico is about 27,000 feet. So it is from 40 feet shallow oil well up to 27,000 feet. So the depth is changing all the time. The first oil well in the world was in Pennsylvania. It drilled in 1859. It was only 70 feet or 69 feet. The other things about the reservoir, you need to know the rocks, because the oil exists inside the rocks of reservoir. The reservoirs rocks are made of three types. Either they call them sandstone and shale. We call them clastic sedimentary. Or it is chemical rocks, and these are the salty rocks such as the anhydrite and gypsum. These are salty rocks. Or the organic rocks coming from the shell of a living organism, such as the limestone and carbonate, which is the dolomite. Dolomite, it is magnesium carbonate. So either calcium carbonate or magnesium carbonate, which we call them the carbonic, or we call them the organic rocks. These are the three types of the rocks which is the oil could be exist inside. If somebody asks you what are usually the rocks of oil reservoir, you tell him either could be sandstone or shale. We have examples on that south of Iraq. They have also in Kuwait, they have sandstone. South of Iraq, they have one of the biggest field in the world. Kuwait also, called Burgan. Burgan is the largest oil field in the world made of sandstone in Kuwait. And sometimes it is made of limestone. The largest oil field limestone in the world is Saudi Arabia, called Gawar oil field, made of limestone. And there's a few very small reservoirs made of salt. They call them the salt domes. Salt domes. I will show you some picture later on. So remember, the name of the rocks where you can find oil and gas in it, either sandstone, shale, salty rocks, or the carbonate rocks, which is limestone and dolomite. Of course, the Oil start in a deep rocks. They call them the source rocks. Source rocks like the kitchen where you cook your oil first. And then after that, the oil will will move from the source rocks to the other type of rocks. A good example of source rocks is shale. So shale has oil. I'm sure you heard nowadays about shale gas and shale oil, which people try to get oil out of it because they are source rocks. After the source rocks, the oil being generated and then move into the other rocks, which is the sandstone or limestone or the dolomite. They move in a process called migration. Migration is movement of oil from the source rocks to the other type of reservoir rocks, which you call them the traps. The other types could be sandstone, could be limestone, could be salt domes, could be shale. And the movement will be either due to density differences, buoyancy, or due to hydrodynamic, which is kind of pressure differences, or capillary actions, which is the capillary movement. And therefore, we change from source rocks to other type of reservoir, which we call the reservoir rocks or the reservoir accumulation. This is buoyancy. So remember, if somebody asks you, how does the oil move from the source rocks to the reservoir, from shale into sandstone or into limestone, either by buoyancy or hydrodynamic or capillary action. For the students, if you have a piece of paper and pencil, make a note of these information because this information does not exist in books. It's come from my experience. So the buoyancy, and then explore hydrodynamics. I will pass very fast. Then that movement of oil from the source and being captured inside the reservoir rocks, we call that a traps. The oil being trapped inside that rocks. The type of the traps could be folding or faulting. As you said, we have fault and we have anticline. Stratigraphic, which is lithology, rocks on top of each other. Or sometimes we have combination, which is a mix between structure and stratigraphies. I'll give you examples here, for example. These are some of the pictures. Number one, you see this one, number one. You see this picture here? We call it a fault reservoir. Fault, yani the rock is being broken and then trapped inside. So you have gas on top and the black area is oil. This type of rocks, if we find it somewhere else, we call it a fault reservoir. Nature, geology. I'm sure the petroleum engineering year 1 and year 2, they teach you some petroleum geology, and also civil engineers, they teach you some geology as well. You know geology, structural geology, soil, and so on. And I'm sure you heard about fault, like an earthquake. Or the number 2, or here number 2 here, we call salt dome. This white shape, look like a mushroom shape, is made of salty rocks, such as gypsum or anhydrate. And the oil will be around the wing of it. Here you have oil. We call it a salt dome. And the third one, as you see, the folding, F-O-L-D, D for door. And this called anticline, like a mountain shape. On the top, we have oil. Underneath, we have water. These are the types of, we call them traps, or you can call them also reservoir traps, which is come after migration. Simple, important, but that's most of the oil field in the world. If we talk about an oil field in Assam, Assam is folding one, fold shape, anticline shape. In Mumbai Bay, there's a lot of them are a fractured one. In other words, the fault one. You have little salt dome in India near Chennai, a small one, not a big one. But most of the oil fields or oil reservoirs in India, either they are a dome shape, we call them the anticline, or the fault shape, which is part of earthquake movement or history. This is the most common one, the fault or the folding one, the anticline. This most of the oil fields around the world. I can say 70% of the oil reservoir around the world look like this shape, the anticline or the folding one, where you have the gas on the top, the oil in the middle, and the water underneath. This is a piece of rock, which we call the reservoir rocks, because it looks like a tank and the oil and the gas inside it. The rocks on the top, the rocks underneath, we don't name them reservoir. The only one we name reservoir is the piece of the rock having the oil, gas, water inside it. The gas on the top, they name it in reservoir engineering as gas cap. The water underneath, they name it as water aquifer. The oil in the middle, we name it as the pay zone or oil zone. The contact area between gas and oil, they name it GOC, gas oil contact. And the contact area between oil and water, they name it as OWC, oil water contact. So that's the reservoir. This is the meaning of reservoir. Our topic today is about reservoir engineering. If I talk about reservoir, this is a typical example of an oil reservoir. It's an anticline, folding one. It has 3 fluid in one piece of rock. On top of it, I have the gas. In the middle, I have the oil. Underneath, I have the water. That is the oil field in Assam, look like this as a geology. The other type of traps, as I said to you, stratigraphy could be sandstone, could be limestone. I think you have that in the west part of India. Near Chennai, you have kind of stratigraphic, small one. And the other type of traps, which we already mentioned them. So we have the anticline, I mentioned them. Fault, I mentioned that to you. Salt dome, I mentioned that to you. And the other 3 other stratigraphic. This is they call the unconformity and the reef, which is the offshore. This is usually offshore. Usually in nature, the largest oil field or oil reservoir is the fold one, the anticline. They are the largest as accumulation, as a reserve. The oil is trapped by movement from the source rocks because of buoyancy, hydrodynamic, and they move. If they don't find any seal rock, they will go out. You can see them on the surface of the earth. We call seep. Seep is the escape of hydrocarbon from underneath to the surface of the land. I have seen that in Iraq, actually. We have so many seeps in Iraq, gas and oil, especially in the north part of Iraq. Sometimes also the oil leaks into the offshore under the sea because we don't have something sealing it. That thing sealing it, we name it the cap rocks. So this rock sealing, we call the cap rocks. If you don't have cap rocks, then the oil and gas will escape to the nature, to the open nature. Because These are the 5 elements in reservoir. In reservoir engineering, this little slide show you the 5 elements in reservoir engineering. First one, you have to have something called the source rocks, where is the oil start to be generated here because of high temperature, pressure, the dead animals living here, so organic changing, and that make it change into liquid. That liquid is the hydrocarbon, and then start moving after that. So after source rocks, we have something called migration. Remember, these are the 5 principles in reservoir engineering. You have to have a source rocks. Then when the liquid is generated, it starts moving because the pressure in the source rock is high. So move from high pressure to a lower pressures. It moves either by capillary, by buoyancy, or by hydrodynamic. And they move until they captured into a piece of rock we call the trap rock. That's stage number 3. The trap, from the name, trap, something being captured in the rock and being accumulated subsurface. One of the most important conditions for a trap, it should have something called a seal. No way to escape. And that's important. In this case, the oil and gas being trapped and no way to escape, I will name this number 5. I name it reservoir. So this is the idea of reservoir, coming from source rock, migration, being trapped and sealed, nowhere to escape. Now I discover a reservoir of oil. That's what happened in Assam, in India, or Northeast India. So the trap is important, otherwise we have escape. Then these rocks, which is I named now reservoir, I named them reservoir. You see the red, the green, and the blue. The red is gas, the green is oil, and the blue is the water. That is the reservoir. It should have 2 or 3 important properties. One, it has something called porosity. Remember, our lecture today is about reservoir properties. So one of the important property in reservoir rocks is to have something called porosity. Porosity is the space where the oil will occupy part of the rock. Part of the rock is an empty part. So the oil will go inside empty area, which we call porosity. And if the oil is moving from source to the reservoir, it moves through a channelings inside the rocks. That channeling inside the rocks, they name it permeability, permeable. So we have 2 important properties in a reservoir rock. One, it should be porous, meaning we have a space. Number 2, it should have channeling. So the oil reserve has a connection with porosity, with porous. And the oil production has a connection with permeability. So this first word has a connection with how much oil in the place, reserve. And permeability has a connection with production and movement. These are important features in the reservoir rocks. You should have porosity and permeability. Porosity, you can measure it as a percentage. We say this rock porosity is about, for example, the sandstone, limestone I mentioned to you already, these rocks I mentioned that already to you. Porosity, so these are important properties. Porosity is a percentage of the rock's voidage or space within the body of the rocks. So if you say limestone has a porosity of 25%, then the space within that rocks is 25% of the volume of it. And maybe some of it, or some of the territory, is occupied by oil and gas. Does the oil and gas will occupy all the porous volume? Sometimes no. It will occupy percentage of them. So porosity is important as a space, as a room to live in, to stay inside it. And then if the oil wants to move, it has to have something called channeling. We name it permeability. Permeability measured in a unit called millidarcy. Millidarcy. As a unit of area, actually. It's a unit area, centimeters square. And the millidarcy is a very small unit. For example, you say permeability in a Assam oil field is 10 millidarcy or 12 millidarcy. Not very much, but they are channeling. Usually, permeability in gas reservoirs are smaller than permeability in oil reservoir. Oil, you talk about 20, 50 millidarcy. Gas reservoir, you talk about 1 or 2 millidarcy. Because the gas is easy to move. Oil is difficult to move. Need more channeling, the oil. So porosity, permeability, and the other property important we call waterability. Waterability is a tendency of oil and gas to saturate the rocks. So I have a piece of sponge. I put it into a pool of water. How does the water move inside the sponge and make it wet? That's wettability. Ability of the oil and gas to be adhesive to the body of the rocks. We will mention that later on as well. The other important property of the rocks, now remember porosity, permeability, wettability. Number 3 is temperature and pressure. And these temperature and pressure of the reservoir will depend very much on the depth. There's an eye window saying the deeper you go, the more the chance for a gas accumulation, because you have high pressure and high temperature. For example, here on the y-axis, the depth in meter, after 4,000 meters, you may find more gases rather than oil. But in a shallow area, you may find more oil. And in shallower area, you find oil, but heavy oil. For example, in Oman, if you get a job in Oman, most of the oil fields in Oman are shallow. They are heavy oil, most of them. But the deeper are lighter. So, for example, in the North Sea, in Aberdeen, we have deep wells. So they give me a lighter oil. The temperature of the reservoir could be up to 220, I can say, degree Fahrenheit. And the pressure of the reservoir is about 6,000 psi. And you can predict the pressure of the reservoir and temperature of the reservoir by a small basic calculation. This is the way to calculate the pressure of the reservoir. PR of a reservoir is equal to 0.433 multiplied by depth in feet. So if somebody say to me, my reservoir is at 10,000 feet, what will be the pressure? You tell him 10,000 multiplied by 0.433 will be 4,330 psi. That's the normal. That's the most normal. Sometimes we have abnormal. Sometimes you have hydrostatic, and sometimes you have a dynamic pressure. But generally, we use the pressure gradient of 0.433. Sometimes could be 0.44, sometimes could be 0.53, depending on the geology structure of the reservoir. But majority of them are between 0.433, sometimes 0.456, 0.456, sometime. The temperature also, you can predict the temperature of the field or reservoir by using this simple equation. This is in Fahrenheit. You say a surface temperature, maybe 70 Fahrenheit, plus 2.6, that's temperature gradient. Multiply by the depth in feet, divided by 100, you will get the temperature of the reservoir. I said to you, usually temperature of the reservoir could be 170 Fahrenheit, could be 210 Fahrenheit, depending on the geological structures. But for sure, the reservoirs are hot, very hot sometimes from the surface. The pressure also very high. So remember this properties of reservoir. We need to know about porosity, permeability, wettability, which is in other words saturation, pressure, and temperature. These are 5 important properties for a reservoir to be understood or to be followed. And we mentioned the reservoir pressure, how to calculate. The rocks, we have mentioned rocks in reservoir could be sandstone, limestone, dolomite, and shale. 4 types of the rocks are very famous and common for reservoir: sandstone, limestone, dolomite, and shale. Most common, sandstone and limestone. Dolomite is less, shale is less. And the properties, we say porosity, the pore volume, and porosity come as a percentage. So it's 20%, 25%. We have mentioned already that things. And this is the way they calculate porosity. I'm not going to show you how to calculate, because I'm not giving you academic lecture. I'm going to give you a training. But you should be, as a petroleum engineer by now, if you are 3rd year petroleum engineering, you should be able to calculate porosity, or know how to calculate porosity. Most of the oil field around the world, porosity between 15% up to 25%. More than that is not good. It would be a loose sand production. We have something called the interconnected, we have effective porosity, we have bulk velocity, we have porosity certainly, we have primary porosity, secondary porosity. You can talk about this very, very much, but for me, no time to talk about it in details. So primary, secondary, effective porosity, absolute porosity, different names you can talk about. These are the slides showing you how to measure the porosity. Sometimes you can use logging for measuring the velour porosity. Sometimes lab work, core analysis, you are using that. So the porosity is important to estimate how much oil in a place and to tell you how much we have a space for oil and gas, as well as the saturation. Saturation of oil in the reservoir is a percentage of porosity. So if somebody said to me the oil saturation is 60% in that rock, that means 60% of the porosity is being occupied by oil. That's the meaning of it. So if somebody, I repeat again, if somebody said to me, we have 60% oil saturation, what does it mean? It means 60% of the porosity is being occupied by oil. That's the meaning of saturation. Of course, porosity has connection with depth. The deeper the reservoir, the less the porosity. So as you go deeper and deeper, we will get smaller porosities because of the compaction. The other important property is for production. And remember now, porosity is good for reserve, how much oil in place, and saturation. Permeability is good property for production and movement, channeling. And permeability, again, tell me about the interconnection channels in the body of the rocks, which will make the oil move from A to B, from X to Y, due to the pressure differences. So the permeability, like a small pipelines inside the body of the rocks, channels inside the body of the rocks. Permeability will measure into a unit called millidarcy, and the millidarcy sometimes is very small unit. Majority of reservoirs are within 10 to 100 millidarcies, most of them. Unless you have fracture, you have big channeling, we call it exceptional, we may get more than 1,000. But normal rocks, they have between 10 to 100. Limestone and sandstone, they have permeability more than the permeability in sandstone. So limestone and dolomite, their permeability is larger than permeability in sandstone, because most of the limestone rocks are fractured. Just a piece of note for you. So permeability is important in movement, oil in the body of the rocks. And they use permeability later on for the calculation of flow. You see flow. So the flow, the movement, has a connection with permeability. But the storage has a connection with porosity. Remember these two words. Make a note of them. Permeability has a connection with flow and movement. Porosity has a connection with storage and capacity. I will continue. This is the way they calculate permeability as a K. And this is the equation used to know the equation of flow inside the rocks. They call the Darcy equation or Darcy law. I'm sure civil engineers, they know the Darcy law. And also petroleum engineers, they know the word Darcy law. Darcy law or Darcy equation, it tells you the movement of oil inside the body of the rocks. Depending on the value of K, a constant conversion factor, the area of contact, pressure differences, the viscosity of oil, and the length, the spacing, the distance is moving. That tells you flow rate, which could be written in a field unit. So if I work in oil field, in Burgan oil field, Rumaila oil field, in Saudi oil fields, and Mumbai Bay oil fields, they calculate the flow rate of oil using this equation. We call it radial flow. And see the K, always K is there. K is, as we said to you, is the letter for permeability in millidarcy. That's what we call it Darcy equation, radial flow. And that's the importance of this property. You cannot have a good oil reservoir with a small permeability or very, very small permeability. As you see from the equation, the smaller the value of K, the smaller the value of oil production, the movement, flow rate. That's why sometimes we need to do fracturing. Sometimes we need to do acidizing, penetration, perforations, just to make the channels. So if the channels inside the body of the rocks is K, and the K is very, very small, your production will be very small. You need higher productions, then maybe you need to do a fracturing or acidizing or perforation or horizontal drilling. K is very important for production. Very, very important. So that's, remember, my lecture with you is about properties of reservoir. One of the most important that's very important for our production to know the value of K. I hope that's clear for you. I will talk about other properties such as viscosity, but I will talk about them in coming slides. So the connection between porosity and permeability as statistics, as a data, as a graphical presentation, there almost there's a fact or a rule of thumb. The more the porosity, the higher the permeability. As you see, these are the lines for different type of rocks, such as dolomite, limestone, another limestone, sand, chalk limestone, grained sand. So you see the sandstone and limestone are the most common type of rocks for reservoir rocks. And clearly you can calculate the K, the permeability of oil or of a gas reservoir, having this equation in front of you. SWC, the connate water saturation, most of the time is a fixed value equal to 0.2, 20%. So you can predict the value, and clearly from the equation in front of you, the permeability for oil reservoir is larger than the permeability for the gas reservoir. You see here multiplied by 62.5, here multiplied by 2.5. Because the gas can move easier and faster because it's smaller. The other property of the reservoir rocks is a compressibility. If I take the oil out from the reservoir, then that reservoir will be subsidized, will be getting lower, crashed down. That's a possibility. Small value, so the rocks could be compressible due to a high pressure on them or due to taking the oil out of them. And these some equations regarding how to calculate the compressibility of the rocks. And this is the total compressibility. So the rocks also compressible. And very important in the offshore engineering to take that in consideration. Give example, these are the subsidies. You can calculate how many inches may that get down. And this example from the North Sea, Statoil Norway side. You see here this platform in 1973 and same platform in 1984 after 10 years. See what happened to that platform, offshore platform, is being subsidized. You see here, if you calculate number of holes, 1, 2, 3, 4, 5, now only 2 appear. So 3 of them come under the water due to the subsidies. Because they produce the oil after 10 years, they take all the oil from the reservoir, no much pressure to maintain the overburden pressures, so that cause some kind of subsidies, which is really a mechanical issue, could damage all the pipeline and damage the casing and cementing and so on. So it's also important property to think about. I repeat them, porosity, permeability, wettability, compressibility. I will come to more later on. These are properties important, a pressure and temperature of the reservoir. So pressure, temperature, porosity, permeability, wettability, and compressibility. 6 properties so far. Make note of them. They are important properties of the reservoir. You need to know them. Tomorrow, if you graduate and get a job as a petroleum reservoir engineer, you need to know these things. Porosity, permeability, wettability, in between bracket saturation, compressibility, pressure, and temperature. Then you take to the properties of the oil itself. As part of reservoir engineering, you need to know the properties of the oil. What is my type of my oil? Is it heavy oil? Light oil? Is it asphaltene? Is it a tar? Is it bitumen? Is it paraffin? Is it acidic or alkaline in terms of pH value? So you need to know these things as properties of the fluid inside the rocks. So you need to know the rocks and the fluid in the rocks. And these some of the properties you need to be aware about. The crude oil exists in the rocks could be classified as a black oil, not the most common things, or the crude oil, natural oil, I can say. The oil we put in the refinery. Or the volatile, which is a very light oil, very, very lighter. Condensate is merely gas with liquid inside it. And then we have the wet and dry gas. So we have 4 types of hydrocarbons exist in the reservoir. Normal one, crude oil, could be heavy or light. Volatile is very, very light, but it has more gas inside it, high shrinkage. Condensate, these are almost gas in the normal temperatures. In chemistry, they made of C5 and C6, pentane and hexane. Or we have gas reservoir. As you say in India, you have so many gas reservoirs around Mumbai and around Chennai, the east. These some properties of black oil, the normal crude oil. The API between 20 to 30, maybe 35, something like that. We call it medium or light. GOR of it is, we're going to talk about GOR. GOR is how much gas will be liberated if you produce 1 barrel of oil. Every barrel of oil you bring to the surface, gas come out of it. We call the associated gas. Some people say the APG, associated petroleum gas. So if they say 500, that means we can produce 500 standard cubic feet for every stock tank barrel. For every barrel of oil I bring to the surface, it come with it or come out of it 500 cubic feet. That gas I call the GOR, or the associated gas. The oil, when it comes to the surface, will be shrink a little bit because gas come out of it. That shrinkage factor, they name it formation volume factor. I want to show you the slide here. Here it is. So this is the formation volume, the shrinkage factor. I have oil in the reservoir condition, pressure and temperature of reservoir. The pressure could be 6,000 psi. Temperature could be 210 degree Fahrenheit. If I bring it to the surface, pressure of the surface, as you know, is atmospheric pressure, 14.7 psi. Temperature of the surface is temperature of the condition, should be maybe could be 60 or 70 Fahrenheit or 80. And therefore, the oil will shrink. So the oil inside the reservoir is larger in size to the oil you bring to the surface. Why? Because this amount of gas came out of it. We call it shrinkage factor or oil formation volume factor, which we name it here in this slide as numbers. We said here 1.5 to 3.5. Shrink, in other words, when I say shrinkage factor is 1.5, what does it mean? It means if I have 1.5 barrel in the reservoir, if I bring it, it will change into 1 barrel only. Half of that barrel being evaporated or changed into gas. That's the meaning of shrinkage factor, formation volume factor. So the properties of the oil, what do I need to know as a reservoir engineer? The answer, you need to know a shrinkage factor, You need to know the API. You need to know the GOR. You need to know the viscosity of the oil. An API is the other face for density. Same meaning. API is high, we call it light oil. Light oil means low density. API is small, mean heavy oil. Heavy oil mean high density. Of course, the oil in the market, they need lighter oil. 35, 36 API and so on. So remember now, as an engineer, you need to know the properties of the oil, which I should be aware about, are API, gravity factor they call it, and API stands for American Petroleum Institute Index. I need to know GOR, formation volume factor is beta naught, and the viscosity. These are 4 important properties. Can I calculate API for the crude oil? The answer is yes. This is the equation for it. Here is API gravity. This is the equation. They call it an empirical equation. No derivation behind it. You just put the data. You need to know specific gravity of oil. Could be 0.6 or 0.7 or 0.8. You this over this, you get it. And according to that, you will classify your oil as a light oil or medium or heavy. So anything more than 37 API, we go to extra light or light or medium or heavy according to the value of API, which has connection with specific gravity. I hope that's clear. And remember, my talk to you is about, our title of my talk to you today, or my speech or my seminar or my lecture is the properties of reservoir. So you need to know properties of the rocks, properties of the oil and gas, and then you need to be interaction as well, interaction between oil and gas and the rocks. So this is important thing you need to be aware about. And these are the shrinkage factor we mentioned to you. This is the way they calculate shrinkage factor, formation formula. When we say it is 1.5 or 2.5 or 3.5, how much they shrinkage, they calculated using this equation. As you see, it has connection with gas solubility, it has connection with temperature, and with the API for oil and gas. This is the behavior. So as we are producing, the volume will increase, and then the gas come out, and that we call it the bubble point pressure. GOR, I mentioned that to you as well, is a ratio between how much gas for every barrel of oil. So volume of gas over volume of oil in the reservoir condition. The solution gas, again, how much gas can be dissolved, and this is the equation for it. We have other properties for the gas behavior or oil behavior called the bubble point, the pressure at which the gas will be liberated. You need to know this. So I repeat again, what do I need to know about my crude oil properties? I need to know the API, density, viscosity, a shrinkage factor, gas solubility, bubble point pressure. I need to know these things about my oil and gas properties in the reservoir, mainly oil properties. Remember, my lecture is about properties. So properties of the rocks and properties of the fluid, mainly the oil. The bubble point pressure, the pressure at which the gas will start to liberate, the pressure will change from RS into GR. RS and the gas is still inside the body of the oil, didn't come out. If the gas come out of the oil, I name it GOR. GOR. When does the gas come outside the oil? When the pressure is less than bubble point pressure. Very simple. Remember these things. How can I calculate the bubble point pressure? Can I predict? The answer is yes. Somebody put equation for us. This is the equation to calculate the value of the bubble point pressure in PSI. PSI absolute. I need to know temperature of the reservoir. I need to know the API of my oil. And I need RS and specific gravity of gas. If I have these data, I will be able to calculate the bubble point pressure, which is an important property for oil. So I repeat again, oil density, API of the oil, solubility of the gas, GOR after liberation, and the bubble point pressures. I need to know them about my oil in reservoir as properties. The other important property we have mentioned already is viscosity. If you remember when I talk about Darcy equation, if I show you Darcy equation again, in Darcy equation, the flow of oil in the reservoir, according to the permeability, we will have viscosity. This is mu naught here. This is Darcy equation, mu naught. You see that? That mu naught, oil viscosity, could be also calculated or could be studied by the reservoir engineer. Remember, this is all part of reservoir engineering. You need to know all these things to be a good reservoir engineer. So the oil viscosity could be lighter, easy to flow, could be heavy, difficult to flow. If you are a mechanical engineer, chemical engineer, I'm sure you heard about viscosity. And viscosity is, if you ask Google, it will tell you resistance of fluid to flow. Resistance of fluid to flow. This is the way they calculate the viscosity. Dynamic. We have two types of viscosity. We have dynamic. We have kinematic. Stoke. Centi-stoke, and we have centi-poise. This is the way I calculate the dynamic one, the movement oil viscosity inside the rocks. This is the way I can calculate it. Again, you need to know the API factor. You need to know the temperature of the reservoir to help you to calculate the value of X and Y and Z. Dynamic, we have other type of viscosity, which we'll call it kinematic, as you see in the y-axis here, centi-stokes. This kinematic viscosity of non-moving oil. The oil is still inside the reservoir, is not moving yet, or inside the tank. When it moves, I will change it into something called dynamic. And there's equation to change between them. This is the equation to calculate or to change. You can change it from kinematic into dynamic, or from dynamic into kinematic by dividing by the density of the oil or specific gravity of oil. I hope that's clear and important for you to talk about movement of oil in rocks. The more the viscosity, the difficult for movement, difficult to produce. That's why sometimes they do something in India, they do it as well. Steam injection. Steam injection. I'm sure you do it in India. Or sometimes you do in situ combustion. You're burning the reservoir or the production, the well, the producing well, to reduce viscosity, to make it easy to flow. So heavy oil needs some time, kind of engineering interaction or intervening by injecting hot water or injecting steam, or you do in situ combustion to produce oil out. These are some of the curves regarding temperature and viscosity. Clearly, the higher the temperature, the lower the viscosity. And that's why people hear also about temperature in the x-axis, kinematic centi-stoke on the y-axis, and different API So if somebody says to me, the API of my oil is about 30, and the temperature of my reservoir is, for example, 50, I can read my viscosity and change it from kinematic into dynamic. And then I decide, shall I do water injection, or shall I do steam injection, or in situ combustion, or something like that. I'm aware about the time, so I need to speed up a little bit. So reservoir fluid distribution now, as a reservoir engineer, you should be understanding rock properties, porosity, permeability, waterability. You need to understand your oil properties, such as viscosity, density, API, gas solubility. You need to understand your rock properties, such as compressibility, pressure, temperature. The other properties you need to understand now, what is the interaction? How does the oil and rocks behave together? How does the oil behave inside the rocks? That is the interaction between rocks and the fluid, oil, gas, and water. That interaction, you can look into more properties such as the zonation, zone. Where does my oil exist? In the middle or on the upper part? The oil-water contact, I mentioned to you already, zonation. Remember when I mentioned this slide for you? And I mentioned some of these names already when I talked about the anticline reservoir. So I need to know, this is zonation. Zone for gas, zone for oil, and zone for water. And I have contact between oil and gas. We have contact between water and oil. I have pressure, I have spill point, and I have thickness of the pay zone, and so on. So these are interaction between oil and gas. I need to understand how does the oil will interact with the rocks. And that could be including saturation, capillary pressure, surface tension and interfacial tension, waterability, which I mentioned earlier, and the contact angle, and the transition zone. So in terms of distribution, or I can say zoning, I have a zone for gas, a zone for oil, a zone for water, and I have contact area between them, WOC, water oil contact, and GOC, gas oil contact, and between them, they have the transition zone. So this transition zone, for example, and I have oil, I have water, and between oil and water, I have some kind of a mix between oil and water. We call the transition zone. If I take a sample here, maybe I have 70% oil, 30% water. If I take a sample from the bottom, I may have 70% water and 30% oil. This is also important part in reservoir engineering to be understood. Remember, my speech with you, my lecture with you is about reservoir properties. So I'm covering everything you think about. Of course, there's calculation behind them, mathematics behind them. I'm not teaching here. I'm just giving a lecture or a training. Maybe in the future, we will arrange some teaching sessions for you in the future. Once we agree with the principle, we may give you a full semester about a certain topics. So the saturation is important. Oil saturation, water, gas saturation. As I said to you, saturation is part of porosity. If somebody said to me, SO is 20%, so 20% of the porosity is filled with oil. If you add them together, it should be 100%. So 20% oil could be 70% water, 20 and 70 is 90, and then 10% gas, 100. So if you add them together, you can finish to a full unit, a complete 100%. And that is what we call it like this. We have like this. Maybe the gas is 10%, the oil could be here 80%, 10 and 8 is 90, and the water is 10% again. Saturation could be, say, critical, sometimes residual, sometimes movable, mobility, but they have different names according to the value of them. Residual and the connate. Connate is not moving, difficult to move. Residual is after production, how much being left behind. So maybe I start with the reservoir as a brand new reservoir, 80% oil saturation. After 10 years, if I measure saturation, it could be now 20%. From 80 to 20, that 20% I can name it as the SOR, residual. If I go less than that, I will call connate. Connate, which is sometimes I leave it. I cannot move it. So movable one is the one which is in the middle, and still the oil is producing. Could be 50%, could be 35%. The other interaction between rock and fluid is the capillary pressures, which has a link with weightability. I mentioned weightability and weighting. Capillary pressure is natural movement of oil inside the rocks against gravity, going up, and has connection with surface tension as well as viscosity and the angle of contact. So it needs some calculation in physics, I can say. The IFT, the interfacial tension between the rocks and the oil, or between the oil and the water, between the oil and the gas, which is also you can calculate the capillary pressures. This is the way to calculate capillary pressures. Is the pressure responsible for the oil to go inside the capillary in the channels. For example, here, the water go inside the channel. So I have a channel and the water goes up against gravity. That distance h, how far it moves, we call the capillary height. And if you know the height and density difference between oil and water and the contact angle, the theta angle, cosine of it, are in the radius of the capillary tube, which is usually a very small number, 10 to the power minus 4 of millimeter. We talk about microns, actually, 3 microns or 4 microns, the radius, with the gravity factor. So against gravity, movement of oil or liquid upward against gravity. That's why you have gravity factor. Capillary pressure is also important later on for water injection, gas injection, movement of oil, migration of oil. It has some connections. So as a reservoir engineer, you need to study this. A capillary pressure, you can make even a master thesis about it, a big topic. And the connection between capillary and the channeling and permeability. The wider the rocks, the higher the K value, which is the permeability, the smaller the capillary pressures. But as the channel is very, very narrow, you will get a high capillary pressures. So the pressure responsible for making the liquid moving upward inside the body of rocks against gravity. That's capillary pressure. And a simple definition, what is capillary pressure? It's the pressure responsible for the movement of oil or liquid or water inside the channels of the rocks upward against gravity. So the smaller the K, the more the PC. The smaller the permeability, the more the PC. And these are some examples of them for the distribution and gradient. As I said to you, it's a big topic. This session is not enough to talk about it, just give you a flavor of. We have something also, if you remember, we have mentioned transition zone. Transition zone, I show you on this slide. I go back to the slide. Transition zone. And then in the transition zone is a mix between oil and water. There's no sharp cut. So also I need to know some time to understand that transition zone thickness and location and other things. One of the ways useful for that is to think about the free water. When shall I get a free water? At what depth? And that is meaning, and this slide in front of you, this blue area under the oil water contact, I can name it as a free water level or free water distribution, or I can say it's 100% water and no transition zone. So the transition zone is the zone that located between the oil water contact and some part of the clean oil. You see here you have a red solid line and a red dashed line, and that area between them I call transition zone. Transition zone is a dynamic. As more you produce, the more the water will go up and the dashed line go up as well. As a reservoir engineer, you need to know where is your location for the free water, because that's important in water injection later on. And has connection with the PC as well, the capillary pressures. So the properties important for me: capillary pressure, transition zone, water oil contact, gas oil contact, wettability as well, interfacial tension, the IFT, surface tension between oil and rocks, also important for me. And these are wettability. Wettability is the tendency of oil or fluid to stay on the surface of the rocks, cannot move easily. For example, you say here, very easy for me to move the mercury, difficult to move the oil, more difficult to move the water. So the smaller the contact angle, the more the difficulty to move. So we say, for example, here, we call it a water weight reservoir. Here I can say non-weightable reservoir. Here it is. If I have the angle less than 90, I will show you a slide here. If the angle of contact is less than 90, I call it water weight rocks or water weight reservoir rocks. That means the rocks love to have the water inside them. They don't make the water moving away. That's very important in the water flooding later on. Or you have this case. You have this case where you have something similar. The angle is more than 90, as you see in this little slide. This is what we call the oil weight reservoir. So here, water weight reservoir, oil weight reservoir. Both of them have some properties need to be understood, and that is very important to take in consideration, depending on later on what you're going to do. Shall I do water injection, gas injection? Shall I do flooding, or shall I leave the well? Do I have water production or no? These are important to keep in mind as interaction between rocks. And we have something called imbibition. That means saturation is increasing by injecting some water, and we have drainage. When I produce oil, so I'm draining the oil from the reservoir. So imbibition, drainage, all these are important for reservoir engineer. Later on the surface, you can do more reservoir working, such as PVT analysis, to tell you how much the gas, how much oil density, oil gas solubility. These are also part of PVT. I will move fast now because of the time. I have only 10 or 20 minutes for that. But remember, these are and PVT are important to tell you the type of the oil, which I already mentioned to you, whether they are a black oil, light oil, heavy oil, the PVT will help you. And PVT envelope, phase diagrams. So these also part of reservoir engineering. So reservoir engineering is a crucial subject in petroleum upstream, and you need to be aware about. I mentioned already this for you, and classify the reservoir as volatile, black oil, gas reservoir, condensate reservoir, and so on. Maybe, as I said, in the future, if we have more time, we will talk about these in details for you. Maybe give you more lectures or maybe a more semester and so on. So fluid flow then, fluid flow inside the rocks will behave according to Darcy equation, which I already mentioned to you. And the Darcy equation, you have to include factors such as viscosity, compressibility, oil density, pressure differences, whether steady state, pseudo, or non-steady states. All these are important. As I said, I cannot cover everything into 90 minutes, but Darcy already I mentioned. We can talk more about Darcy equation in the near future and how to use it in our oil industry for both gas and oil, as well as for linear and radial. I mentioned these already, so it's very good. Actually, I covered some of them. I just want to come to the final part of my lecture. That is the derived mechanism. From nature, the oil can come to the surface by some mechanism inside the reservoir. We call it primary recovery. And these could be a gas cap or water derived underneath, and that will give you the recovery. For example, here, example in front of you here, I can say in this reservoir in front of you is a combination of a gas cap energy as well as the water, the blue one energy. Combined together, that will help to make the oil move to the surface because they have too much pressure inside them, and they push the oil to the surface once we finish the drilling of the well. And that's called water derived. Again, they have something called the gas cap derived and water influx. All these are important actually, and unfortunately cannot cover them into only 90 minutes. The gas cap, again, we have something on the top of the oil like this. We have a gas cap that has energy inside it. It wants to expanding than pushing the oil inside the producing well. That's an energy, natural energy. Sometimes also you have dissolved gas, you have gravity, and so on. If the natural mechanism is depleted and we have no more energy from the nature, what shall I do? The answer, you put something called EOR, enhanced oil recovery. The engineer tried to inject the energy inside the reservoir, inject water, inject gas, and we call it in this case secondary recovery or enhanced oil recovery. EOR stand for enhanced oil recovery by the intervention of reservoir engineer. So you are, as a reservoir engineer in the future, you should also could be having understanding for EOR. And I'm sure, or I'm assuming that in your college, they teach you some of these topics. So that barrel of oil, maybe 25% you produce by having the nature. What nature? Water derived, gas cap. Or secondary. What's the secondary? Secondary is the OR, water injection, gas injection. And the remaining by tertiary. What tertiary? I inject surfactant, polymer, steam, hot water to get the remaining oil. So 25 and 20, 45%. The remaining 55%, I may recover 30% of them or half of them by using steam injection or chemical injection. And these are the tertiary EOR. You see tertiary, this is the tertiary list. You choose the list suitable to your reservoir. Shall I do steam? Then how do I do the steam? Shall I do bacterial, what they call MER, microbial enhanced oil recovery? Shall I do CO2 injection? Shall I do alkaline surfactant polymer? Shall I do surfactant only, polymer only, and so on? So you have a menu of EOR method could be suitable later on. Also, part of the reservoir engineering job is to know how much oil in place, and there's so many methods to go through them. I have no time to cover them all, but simply you need to know porosity. Remember, reserve has connection with porosity. I mentioned that earlier. So porosity is pi is connected to reserve. Could be an easy equation like this, or could be very complex equation. We call the MBE equation like this. A big equation like this one. This is more accurate to give you exactly how much initial oil in place. N, capital N here is how much oil in place. You can use this equation to estimate how much oil in place, and that's important too, and you can modify as well. I think I'm coming to a conclusion now, which is at the end of the day, your understanding for your reservoir need from you a good technology, a good mathematics background, a good geology understanding, physics, and by this it gives you a good understanding for the reservoir to be understood. If I change this slide into a thank you slide, and I say every time for question and answer. So I thank you very much for listening. I hope I deliver the message for you. And now I can open session for maybe 10 minutes or so if you want to ask me. So thank you very much. Paradash, now the mic for you.
Yes, sir. Thank you very much, sir, for sharing your valuable knowledge and experience in the reservoir engineering. Now, students, the Q&A session is open. You can ask the question directly, sir. Unmute your mic.
You can raise hand or you can ask as well. Okay.
One of the questions asked by Vishnu, how does pore structure influence the connect water saturation?
Yes. What the question is? Sorry, I couldn't understand.
Vishnu, can you unmute your mic direct to ask the question to sir?
Yes, sir. Good afternoon, sir.
Afternoon.
Sir, my question is related to pore structure, basically for connate water saturation. So, how pore structure influence the connate water saturation? As we know, the connate water saturation is not removable.
Yeah. The connate water saturation will never ever remove, always stay there. It's part of the geological phenomena. And it could be estimated about 20%. So whatever you do, the water remain there. The pore structure here, or the pore porosity structure, has a connection with that depending on the size of porosity, size of the pore. The smaller the size of the pore, the more the chance for coinate water to be non-movable at all. So the most important factor is the size of the pore volume. Number two, heterogeneity. If that permeability is not fixed value, is changing all the time from one location to another, that also will encourage coinate water not to be moved. So remember, pore volume size, heterogeneity, number three. Number four, a clay content. The more shell content, the more shell volume or clay content in the body of the reservoir, the more the chance for coinate water not to move. The three factors affecting on it: pore volume or pore size, heterogeneity, and number three is a clay content. I hope I answer you.
Yes, sir. Thank you.
Thank you. Great. I can see now people are start to leave. I hope the students has learned something new, something useful for them. My message for you, as most of the audience are students, is like this. Number one, you need to teach yourself sometime. You need to educate yourself. Don't depend only on the lecture notes. So go and read more and more. Number two, try to enhance your mathematics, physics, and chemistry knowledge, useful sometime for understanding reservoir engineering. Number three, increase your skills. You should be a skillful student. Should be able to do presentation, able to be a debatable questions. Don't shy. If you are a shying person, you'll never learn. Ask and try to learn. Read, not for the sake of passing the exam. The exam is very important, yes. You need to pass the exam. But read for the sake of learning. Read to learn, not to memorize or not just all passing the exam. No, read to learn. You are the future. You are the future of your country. Today you are students. Tomorrow you are an engineer on site. About 1.3 billion nationals in India, could be only 10% are engineers. The 90% are non-engineers. So you are among a small portion of the country. Therefore, you are a valuable person as engineer. And I encourage you very much to educate and to teach yourself. Come with new ideas, think, involve in the classroom, involve in the lab. You should be proud of yourself because not everybody is in engineering college. Some of us couldn't come to the college at all. They have no a good grades or they have not enough money to pay for the colleges. So you are lucky in a college and you are lucky into an area with oil and gas, Rajasthan. And your degree later on, your bachelor later on could open doors for you to work abroad. Maybe you get a job in Iraq or maybe in Abu Dhabi or somewhere else, Kuwait, Saudi Arabia. So be proud of yourself, but to compete with other, you have to be a class A, student number A. The market is very competitive. The piece of paper is not enough. You say, I have a bachelor, this is not enough. What else you have? You have skills? Are you good in simulation? Are you good in IT applications? Are you good in communication? Are you good in presentation? Are you good in debating? Are you good in calculations? Are you good in and so on? So enhance your skills as well to be a competitive graduate. Finally, I would like to thank the principal of the college to attend and to support me, and thank for Visual to start that from the beginning, and Barakash to manage the session. And I wish you very good luck.
Yes, thank you, Walter.
Thank you. The principal, you need to say something?
Yes, sir. I told Prakash that you say thanks to sir on behalf of the engineering college.
Thank you. Thank you. As you know, a short time, just introductory time. Maybe in the future, we do more and more.
Sure, sir.
In the future, we have more collaboration. I already spoke with my colleagues in my academy about you, about your college, and they are willing to support you in the future.
Thank you, sir.
Thank you.
Because we discussed with you and finalized the next program.
Yeah, we can agree on next steps. I mean, if you remember, we agreed to send me emails. So tell me in the emails what it will be more beneficial for your students or for your staff, and I will work on it. I have a session in 28th of May. It's a nice session called After Graduation. What shall I do? If I graduate, what shall I do? How can I get the proper job for myself? What do I need to be a successful graduate? I may send you this link later on as well, 28th of May. And any of your students want to attend, they are most welcome.
So you share the link, so our student and faculty definitely join, and I am also joined that program, sir.
You're welcome. You're welcome, inshallah.
Yeah. So Prakash or Vishnu take the link from you and circulate among the group, so everybody join that group, sir.
No
On
problem.
28th.
Yes, sir. There is some question in chat box. Also do this.
Yes, I think Barakash already recording, so he maybe share the record with you, and I will send to, because I have the email of the principal, I send the principal the slides, so he can also share the slides.
Okay.
Yes, sir.
Okay.
Sir, Dr. Hussain, sir, one of the question asked by students in the chat box.
What is
Sir,
it?
Yes, question from asking to the Lalit Solanki. Sir, what is the gas hydrates and what is the difference between the gas hydrates and cell gas?
Gas hydrates is a combination of natural gas with liquid water at high pressure and low temperature, and look like a sponge, look like an ice. And that is usually as a reservoir. And I think I have mentioned this in my previous lectures somewhere else. So the gas hydrate is a physical solid combination of gas with liquid water at a high pressure and low temperature, which is sometimes very difficult to produce. In India, you have some hydrate accumulation near to Chennai, between India and Sri Lanka. Between India and Sri Lanka offshore, there is a good accumulation of hydrate. So the hydrate is not a gas; it is a solid gas mix between methane and liquid water. I will share with you. Sorry. If I can share with you the slide I have, if I can, because this technology is difficult for me. You see this slide? You see this slide? Do you see Parakash?
Yes, sir.
Yes, sir.
You see this icy shape? This icy shape is like an ice. This is the hydrate. So usually is a big piece of rock, solid rock, mixed between water and hydrocarbon, look like an icy shape. We call the hydrate, and that exists in, I think you have it in India. This is India. Where is India in this map? Somewhere should be here. Yeah, should be here. So
Yes,
in India, they have some hydrate anyway. Yeah. And therefore, that the other one he talked about the gas, no, it's natural gas phase, yani liquid gas phase actually. The hydrate as a chemistry, this is the hydrate as a chemistry. It has, you see this yellow one, the yellow is the gas, and surrendered by some kind of crystal water. We call the gas hydrate. I hope that answered him.
Yes, sir. Thank you so much.
Thank you. So I will leave you now in peace, as I said, and maybe in the future, once the principal arranges something, we will do more work with you.
Yes, sure, sir.
I told the principal once the pandemic of Corona is finished, I may visit you also in the visit in India, because I'm a consultant with ONGC anyway, and I come to India quite often.
Okay.
So if the chance allow me, if pandemic and COVID is getting easy and easy, hopefully, we will visit you. So mentioning COVID, I ask everybody to be very careful, maintain the social distance, maintain your mask, and that's very important just to avoid this type of nasty virus.
Yes.
So I thank you.
Thank you, sir.
Wish you good luck, and we'll be in touch.
Yes, sir. Definitely, sir. We will work on your all things about to sharing this valuable knowledge and about the experience in the students, and we will connect to in future, sir.
Inshallah. It's my pleasure, and we will do more work in the future. So very good luck
Yes.
for all of you.
Yes,
And
sir.
the students, as I said to you, work hard.
Yes, sir. Definitely.
Okay, thank you very much. I will say
Thank
bye-bye.
you, sir. Thank you very much. Thank you, students and principal, sir, for attending the webinar.
Thank you.
प्रकाश सर
Yes, Vishnu.
तो सर ये स्लाइड वगैरह अगर आपको मिल जाए ना तो एक बार मेरे को
Yes, sir. Definitely.
ओके और ये कितने